Alright, let me continue with my my series on how I go through AP Physics 1, and this particular topic area is going to cover what I call Unit 3B, which is the energy aspects when we're dealing with an object that has an unbalanced force acting on it. Now, I like to explain energy, or keep in mind that energy is a property. It's a property that something that an object needs in order to do work. And work is a process. So a lot of times my analogy might be energy is money. It's something that we have, that we can use, that we can transfer from one person, from one place to another. The process associated with this then would be getting money or spending money. So birthday money or going out and buying something. And so that's how I like to look at the energy-work relationship. A couple of things before we move on. Both energy and work, they have the same unit, which shouldn't be surprising because they are related, and those units are the joule. They're both scalars, which means there's no direction associated with them. There is simply a magnitude. The energy is always positive. We cannot have negative energy. Now, with that being said, work can be positive or it could be negative. It depends upon whether we're adding energy to an object, then that's positive, or whether the object is using energy, then that's going to be negative. So, in other words, I might refer to adding energy as doing work on an object, do work on a body, and if the body is doing work, body is doing work. And so the difference between positive and negative energy is related to what is doing the work. Are we doing work on the body, or is the body doing work on something else? Alright, let's look at this idea of work a little bit more. Work is when we apply this force, and this is our net force, this is our unbalanced force, and we cause something to move some displacement. In other words, let's say we have a box, and we're going to apply a force to that box, and that box, while we're applying this force, moves some displacement. We're applying this force during the displacement. That's the work. The force is doing work on the box. So what's going on here is that we're transferring energy to the body. Work is a transfer of energy. And that's an important idea to understand. Transferring energy to the body. Alright. Now, work is change in energy. In this case, since we're causing the body to move, work is our change in kinetic energy, which is final kinetic minus initial kinetic. And this is really important to recognize a little bit when we're dealing with work and kinetic energy, because if final kinetic energy is greater than initial kinetic energy, and this happens when our final velocity is greater than the initial velocity, then what this is the positive work that I was referring to a few minutes ago. We're doing work, we're adding energy into the body. If final kinetic energy is less than our initial kinetic energy, then what that means is final velocity is less than initial velocity. This is our negative work. And what's happening here is that the body is doing work on something else. Energy of the body is going up with positive work. energy level of the body is going down with negative work. And these are some of the relationships that you need to be able to recognize. And quite honestly, this is the biggie. Work is a change in energy. Let's look at another example of doing work besides pushing a object horizontally. Let's also look at when we're lifting a body. So when we're lifting the body, work is force times our displacement. In this case, our displacement is vertical, delta y. When we lift a body, an object, the force that we are applying is basically just enough to offset the force of gravity. And the force of gravity is mg. So the work that we're doing is equal to the mass times the acceleration due to gravity times delta y. Well, the potential energy of a body, and we abbreviate that as UG, this is our expression for potential energy, because when we're doing work, in this case, since we're lifting it up, we're changing the gravitational potential energy. One thing to keep in mind here, we just use 10 meters per second squared. We don't use the negative sign. The only time we use the negative sign with the acceleration due to gravity is when we're doing the kinematic equations and we're using g as a vector. So now that we've talked about how work affects the kinetic energy, and we've talked about how work affects the gravitational potential energy, this brings me into our next big topic area, and this is one of our fundamentals, meaning that this is something that we go back to throughout this course a lot of times, similar to Newton's laws, and that's the conservation of mechanical energy. Now, whenever we have a conservation law, what this means is our change in mechanical energy is zero. This is only true if we have a closed system. This is really important to be able to recognize when we're dealing with a closed system. The system is closed when there are no outside forces doing work on anything in the system. No outside forces doing work. In other words, there's nothing external to the various objects that we're looking at that is either adding energy or taking it away. I talk more about systems later on in a unit where I look at multiple objects interacting. So, but back to conservation of mechanical energy. The change in mechanical energy is zero, and so our initial mechanical is equal to final mechanical. And since mechanical energy is potential energy and kinetic energy, what this expression is equivalent to is that our change in gravitational potential plus our change in kinetic is zero. I tend to begin doing conservation of mechanical energy problems as saying my initial gravitation potential energy and my initial kinetic energy is equal to my final gravitational potential and my final kinetic. And this is the expression that I use. And so if we're dropping an object, then initial kinetic energy is zero, and we're looking at it going down to hit the floor, then my final kinetic energy is zero. Cross out just the values that are zero, put in my expressions for gravitational potential and kinetic, and then we just start solving what the problem is being asked for. Keep in mind, this is only for a closed system. So one of the questions that comes up a lot during the course of class is, when do we use it? How do we know energy is being conserved? Besides the fact that it's a closed system, when do we use conservation of mechanical energy? And so some of the indicators that I tell the kids is velocity changing. Do we have a change in velocity? If velocity is changing, kinetic energy is changing. Do we have a change in height? Is it going up or coming down? If we have a change in height, then potential energy is changing. And if we have both of these going on, and we have a closed system, no external forces, primarily friction, we have conservation of mechanical energy. Okay, another topic area related to energy, besides work, conservation of mechanical energy, is this idea of power. This isn't necessarily talked about a lot, but you do need to be familiar with the idea of what power is. Power is the rate work is done. Now, since work is the transfer of energy, this is also the rate energy is transferred. Transfer, there we go. Close enough. So, how to calculate power, we take power is a capital P, we take work divided by time. This is the same thing as change in energy divided by time. The unit for power, well, work is a joule, time is a second, and so that gives us the unit of power, which is the watt. Might have probably heard that term with some of the household appliances or something like this. Power is a little bit of a confusing idea. So let's look at a situation. Let's say we go down to our school track and we walk a lap around the track, 1/4 of a mile. Let's say we then run a lap around the track. In both cases, we're going to do the same amount of work. We're going to apply a force, the same amount of force to move our body for the same distance, 1/4 of a mile. However, when we run, time's much shorter. And so we're going to do the same amount of work in less time. Here is more power. So sometimes, I like to describe, or I might describe power as the effort that you put out into something. If you put a lot of effort into it, you're putting a lot of energy for a short period of time. And so power is just one of these topic areas that tend to come up a little bit on a multiple choice question. It comes up actually more with electrical circuits where we're talking about the rate energy is transferred, which I'll talk about more when I get to that topic area. But it's something that I always cover right now as well. All right, let's talk about our last little topic area that I cover with this unit, and that deals with what I refer to as energy graphs. I love graphs because I think they're very important to understand, and we tend to see them a lot. So there are two types of energy graphs that we can run into. We might run into energy as a function of position, and this is typically as a function of vertical position. And so when this is basically a ball is falling. And so maybe we start up here, and I might do this a little backwards, and if this is 0 and if this is 10 meters, we start with the ball falling at from a height of 10 meters. What we begin with, all our energy right here is gravitational potential. When we end with, at the floor, is no gravitational potential. When we're at 10 meters up in the air and we're just holding it there, we've got no kinetic energy. But then when we come down here and just before we hit the floor, we have lots of kinetic energy. And so these are my 4 points on the energy versus position graph. And what I want to keep in mind is that gravitational potential energy is mg delta y. And so gravitational potential energy is proportional to y. And it's directly proportional. So I'm going to have a linear line as I go from initial gravitational potential to final gravitational potential. Well, as it turns out, if I have a closed system, my total energy, this is my total energy line. That means my kinetic energy is also going to be a linear line, which wasn't too good, sorry about that, but you get the basic idea. Now, the other type of graph that we might run into is an energy versus time graph. And so, excuse me, again, we might be holding something up in the air. We have a lot of gravitational potential energy. We let it go. At some point later on, we have no gravitational potential energy because it hits the floor. At time is equal to 0, our kinetic energy is 0. And then later on, right when it hits the floor, we have our final kinetic energy. And again, this is our total energy line. Now, how we connect the points, though, is a little bit different. Because here, what's going on is kinetic energy is 1/2 mv squared. One of our kinematic equations relates initial to final velocity with the acceleration. If our initial velocity is 0, then my final velocity is acceleration times time. The kinetic energy expression, I plug in AT for velocity, and what I end up with is 1/2 m a squared t squared. What this is telling me is that kinetic energy is proportional to time squared. So that's a much different relationship than a linear relationship. And so my kinetic energy function might look more quadratic. So now my potential energy function is basically a flip of that. And so it's really important to keep in mind when we're looking at energy graphs which one we're looking at. Are we talking about energy as a position, or we talk about energy as a function of time? And then which expression is going to help us determine what the relationship looks like. I think this one right here, the energy versus time expression, is pretty tricky, and you just got to be a little bit careful about that. So with the energy unit, this is all the material I cover. The last unit in Chapter 3 is what I call Unit 3C, Momentum, and that'll be coming up next.